Okay, so I'm going to try to keep this video fairly short because this material is trying to condense it and make it as simple for you to understand as possible. So this is going to talk about the tyrosine kinase situation as well as pKa and pH. So we can start by, the pKa and the pH and what's the deal with all of that. And it's really, really fairly simple what's going on with pKa and pH. Basically what that means is that there's a negative log of the acid ionization constant. Acid ionization constant, that's what pKa means. And what pKa basically means is it's the ability of an ionizable group of an organic compound to donate a hydrogen proton in an aqueous medium. So it's the ability of a group of organic compounds, which for what we know could be, a peptide bond of, amino acids. It's the ability for them to donate a proton in an aqueous media, which means water. Water is aqueous. So this is all happening probably inside the cytoplasm, basically. So when a protein is in a solution where the pH is below the pKa of a particular amino acid residue, the amino acid means it's protonated. And what does protonated mean? Protonated basically means that it adds a hydrogen. That's all that protonated means. So what does that mean? When a protein is in a solution where the pH is below the pKa of a particular amino acid, the amino acid is protonated. So say when the pH of the solution is below the pKa, it means it protonated. So say the pH of a situation is 7 and the pKa is 10. That means that amino acid has protonated. So that's all that what it basically means is it's just a matter of protonation. So if the pKa is 10 and your pH is 7, it means there's protonation going on. If the pKa is 10 and the pH is 11, say, that means there's no protonation going on. So that's just basically what that means. So obviously hydroxyl groups, which is OH, they're a little bit more reactive, and they make amino acids that contain them a lot more reactive. And these hydroxyl groups, they can be phosphorylated for different activities and all of that, and you'll just learn that down the line when you're trying to learn your amino acids. Really very simple. So now we're going to talk about something a little bit more complicated, which is the different domains and how they work with and how they communicate with tyrosine and kinase. So that's coming up next. So with tyrosine and kinase, this is a pretty complicated topic, but it doesn't have to be. Basically, what that means is for us to understand how these proteins work, we need to understand the definition of these domains before we do anything else. So proteins communicate with one another through their interactions, and these interactions are possible through domains. So assuming you know what each domain does, you may be able to guess what the function is. So there's 3 domains that we're going to be working on, which is SH3. And what's SH3? SH3 basically works in binding polyproline regions. That's what SH3 does. What does SH2 do? The SH2 binds to phosphorylated tyrosine residues. And then there's the kinase domain. And what that basically is, it phosphorylates proteins or lipids. So that's basically what the kinase domain does. So in an example of a protein with multiple domains and how they might function together, this might be the kinase domain. So let's draw this out. So this might be, say, the kinase domain. And you got You got a protein going around like this. And then you got your tyrosine here. And tyrosine here. And then you have your SH3. And then you have your SH2. And this SH2 is binded to the protein, the phosphate. What happens is, when this phosphate removal happens, so say we got rid of this phosphate, what happens is it loosens the entire protein. And when this part of the protein moves away from the blue SH2, a lot of different things are going to start happening. So when the site is free, it starts to bind to a phosphorylated tyrosine, and another molecule can bind. So when it binds to a phosphorylated tyrosine, what did we learn that what tyrosine does? It's basically, so SH2 binds to phosphorylated tyrosine residues. So that's what happens. So when we remove the phosphate, it loosens the entire structure. So when this structure is all loosened up, this site is free. So now you can bind to a phosphorylated tyrosine in another molecule. So that's what that basically means. So the SH3 domain binds with polyproline regions, the SH2 domain binds to phosphorylated tyrosine residues, and the kinase domain phosphorylates proteins, lipids, and such. And that's basically what that means. So every time proteins move or change, it can affect how other regions of proteins are affected. And that's where the activating ligand comes in. So what the activating ligand basically is when a protein binds to SH2, it also has a region that binds to SH3, obviously, right? So every time a protein moves from one area or changes, it can affect other regions, right? So when a protein binds to SH2, it also has a region that binds to SH3 domain. This activates a change in conformation. Remember, change in structure, change in function. So this activates a change in the conformation around the protein in the kinase domain. So that's basically what that means. So you can alter these proteins with these domains to do other things. So that's basically all that what it means. So when the binding of the activating ligand, it activates the kinase domain to phosphorylate tyrosine residues, and the kinase can now phosphorylate tyrosine residues. And then the phosphorylation of these tyrosine residues causes a loop to move causing full activation of kinase. So remember that. So when this kinase can phosphorylate these tyrosine to self-activate, the phosphorylation of tyrosine residues, it causes a loop to happen. And that loop can move, causing full activation of kinase, what that basically is. So at the end of amino acids, what have we learned? So we've basically learned that proteins, they regulate activity in time, and things can be turned on and off, and they spatially activate proteins when and where you want them to act. So one of the main things of protein structure is they regulate activity, and this activity can be temporal and spatial. So what does that mean again? Temporal means the activity in time, when in time their things are turned on and off, and spatial means when and where you want them to act. And then there is specificity of activity. That just means that proteins that we are activating work on the correct structure. So specificity, so specific. So specificity of activity, it acts on the correct substrates, whom to have based on the structure. So that's pretty much it for amino acids. The next thing we're going to talk about is membranes, and that's going to be coming up pretty soon. Okay, bye.